Hi everyone. In this talk, I'm going to talk about faster deterministic distributed algorithms for maximal independent set and approximate matching. This joint work together with my PhD advisor, Mohsen Ghaffari. Let me first start with motivating why we're interested in solving maximal independent set in a distributed manner. MIS is a fundamental symmetry breaking problem. It's very easy to solve sequentially. There's a simple greedy algorithm. However, it's much more challenging to solve it in a distributed manner. So why is it fundamental? So first, various problems directly reduce to it. Examples include maximal matching, delta plus 1 coloring, and 2 delta minus 1 edge coloring. Second, various algorithms rely on maximal independent set computations as a subroutine. Examples include the parallel low-Wash local lemma algorithm by Mohsen and others, and also more recently algorithms in learning theory. There has been recent exciting progress on efficient deterministic algorithms for MIS, starting with the work of Mohsen and Ghaffari in 2020. Tools and ideas developed for finding efficient deterministic algorithms have found various applications for other problems. Examples include parallel approximate shortest paths, low-stretch spanning trees, and L1 embeddings, which are all problems which are very different from maximal independent set. Let me now introduce the local model of distributed computing that we consider here throughout the talk. The input is an undirected graph G, where each vertex corresponds to a processor equipped with a unique ID. Each edge corresponds to a communication link between two processors, where messages can be exchanged. It's important to note that G not only serves as the communication network, but it's also the problem instance itself. So if you want to solve maximal independent set, and we want to find an MIS on the graph G, while G also serves as the communication network. Computation proceeds in synchronous rounds, where in each round a processor can first perform some local computation, then it can send a message to each of its neighbors, and third, it in turn receives a message from each neighbor. The local model is very powerful in the sense that it allows for unbounded local computation and unbounded message sizes. As a result, each problem that can be solved can actually be solved in order diameter rounds. Why is that? First, each node can learn the whole graph in order diameter rounds. That's a consequence of the unbounded message sizes. And then second, once a node learns the whole graph, because of unbounded computation, it can solve locally any problem it wants. In general, the solution has to be outputted in a distributed manner. That means each vertex needs to know whether it's part of the maximal independent set or not, but it doesn't need to know the global solution. Now let me talk a bit about the history of maximal independent set. So there's a simple randomized order log n round algorithm by Luby from 1986. And this motivated Lineal's question 1 year later. Does there exist a polylog n round deterministic algorithm for maximal independent set? This was only answered more than 30 years later by Mohsen and Ghaffari in 2020 by giving a polylog n round algorithm. By now, we actually know two different methods how to obtain such a polylog n round algorithm. The first method leads to a roughly log cubed n round algorithm via so-called low diameter decompositions. Second, one can obtain a log cubed n round deterministic algorithm via so-called local rounding. So while these methods are very different, it's curious that they both lead to roughly the same round complexity. Also, even for the easier problems of maximal matching, delta plus 1 coloring and 2 delta minus 1 edge coloring, nothing better than a log cubed n round algorithm was known before our work. Now let me tell you about our results. So first reminder, so previously there was a log cubed n round algorithm via either low diameter decomposition or local rounding. And we now get an improvement by giving a log square n round deterministic algorithm for MIS. This comes closer to the log n over log n lower bound by Baliuk, Brandt, Hirvonen, Olivetti, Rabi, and so Miller. As a corollary, we also directly get this improved round complexity for maximum matching, delta plus 1 coloring and 2 delta minus 1 edge coloring. Even more, we even obtain faster randomized algorithms due to the shadowing framework. So for example, we get a log n round algorithm for delta plus 1 coloring. The main idea of our approach is that we combine both of the previously mentioned techniques. So our algorithm both uses low diameter decompositions and local rounding. In this talk, I'm going to illustrate the two main ideas by giving an algorithm for constant approximate matching. So I'm not directly going to talk about maximum independent set, but the main ideas will still be present in this algorithm. Okay, let me give a brief overview. So in the first part of the talk, I will overview the two known approaches. This will lead to a constant approximate matching algorithm in roughly log square rounds by low diameter decomposition, and a constant approximate matching algorithm in roughly log square delta rounds via local rounding. In the second part, I will then show how we can combine both of these ideas to obtain an improved round complexity of log to the 4/3 of n. Now let me start with low diameter decompositions. So there are various different but very related notions of low diameter decompositions. So let me just give you one notion, but yeah, various others exist. So one notion asks to partition the vertices into clusters, such that each cluster has diameter at most d, where d is some parameter, and at most half of the edges are in between clusters. So here you can find the partition given by the purple clusters, and drawn in green are the intercluster edges. And we want that at most half of the edges are green. Why is such a decomposition useful in a distributed setting? Intuitively, it's useful because it reduces essentially the diameter from some arbitrary value to d. Because in each cluster, we can brute force an optimal solution in order d rounds. In the randomized setting, there exists an algorithm running in log n rounds, producing a diameter of order log n. And this diameter of order log n is also the best possible existentially. This by an algorithm by Miller, Peng, and Xu. On the deterministic side, for a long time, the best round complexity was 2 to the order square log n, and getting a diameter of 2 to the order square log n. This was then improved by Mohsen and Ghaffari, which they gave a polylog n round algorithm with a diameter of log cubed n. The current state of the art gets roughly a diameter of log n, so roughly the same best possible, with a round complexity of roughly log square n, up to polylog log n factors. Now, if we want to use low diameter decompositions to compute a constant approximate matching, we need a slight variation of the low diameter decomposition, which does not ensure that half of the edges, at most half of the edges, are in between clusters, but intuitively speaking, half of the matching, so that we can safely remove these edges. But it can be computed in the same way. Okay, now let me talk about the constant approximate matching algorithm by low diameter decomposition. So the first step is to compute the low diameter decomposition with diameter roughly log n. Then in the second, so like here, in the second step, we remove all the intercluster edges. And this reduces the matching size by at most a constant factor from the guarantees of the low diameter decomposition. Third, we now compute a maximum matching in the recycling graph in log n rounds. And the reason we can do it is because each connected component has a diameter of roughly log n. And then the resulting matching is a constant approximate matching in the original graph. Okay, so this concludes the approximate matching by low diameter decomposition. Now we're going to see how we can use local rounding. So first, let me give a general overview. So local rounding was first applied to matching, and later it was applied and generalized to various other problems. For example, coloring and minimum dominating set. More recently, it was also used to de-randomize, very informally speaking, pairwise independent sampling, where you sample, let's say, every node, but pairwise independently. This led to improved algorithms for maximal independent set cover, and the low diameter clustering algorithm mentioned before uses internally these local roundings. The general approach in local rounding is as follows. As a first step, you compute a good fractional solution. What's a good fractional solution depends on the concrete problem, but often this is much faster to compute than an integral one. And in the second step, you gradually round this fractional solution in multiple rounding steps to finally obtain an integral one. And each rounding step only incurs a minimal loss, so that at the end you have a decent integral solution. So now let's see how this applies more generally to constant approximate matching. Let me first start with the definition. So an assignment, a fractional assignment x, assigning each edge some weight, we refer to it as Q integral, where Q is a parameter, if each edge is assigned a weight of either 0 or at least Q. And if it's assigned a weight of at least Q, then it should also be a power of 2. And we also define mu of x as the matching size, so the fractional weight of that, of x. So here in the example on the lower right corner, x is 1/4 integral, and the matching size, the fractional value, is 3.25. Okay, so now I'm going to talk how are we going to round this fractional solution, and we assume without loss of generality that the graph is bipartite. So first step is we compute a constant approximate 1/2 delta integral solution, and this can be done in order log delta rounds by a simple algorithm. Next, we perform order log delta rounding steps, and after we perform these rounding steps, we obtain an integral matching n. Before I'm going to talk about what each rounding step does, let me give an example. So here on the bottom right, we start with a 1/4 integral solution, and after one rounding step, we turn this into a 1/2 integral solution, and the matching size can slightly decrease, but not too much. So it went from 3.25 to 3. And then after one more rounding step, we finally have a 1 integral solution. And a 1 integral solution is nothing else than just a matching. Okay, so what do we want in each of these log delta rounding steps? So first, each rounding step increases the integrality by a 2 factor. So we start with 1/2 delta, then we go to 1/delta, 2/delta, and so on. So after log delta rounding steps, we indeed obtain an integral matching n. Moreover, each rounding step ensures that the matching size can decrease by at most a 1 - 1 over log delta factor. And why is this useful? Because we have order log delta rounding steps in total, and in each step the matching size decreases by at most a 1 - 1 over log delta factor. Hence, at the very end, we still have a constant approximate matching, but this time it's integral. Moreover, each rounding step takes order log delta rounds. Therefore, the total round complexity is order log delta rounding steps, each taking log delta rounds, so log square delta. And there's also a negligible order log star n rounds that we need for pre-processing. Okay, so this finishes the description of constant approximate matching via local rounding, which gives a complexity of roughly log square delta. Now I'm going to talk about how we obtain a constant approximate matching in roughly log to the 4/3 n rounds by combining both of the previously seen techniques. The key lemma that we're going to show is the following. So for every alpha at most log n, so alpha is a parameter that you can choose freely, one can compute a constant approximate 0.5 to the log n over alpha integral matching in roughly alpha times log n rounds. So the first observation for this lemma is that assume you set alpha equals log n, then this lemma actually produces an integral matching, and the round complexity is roughly log square n rounds. So this lemma generalizes what we have seen, what we can get from the low diameter decomposition approach. However, later we see that we actually can set alpha smaller, and this will thereby gain something. So it's trade-offs the integrality that we obtain and the round complexity. Okay, so why is this useful? So first, we can remove all the zero white edges in the graph from this fraction matching we have computed, and this drops the matching size by at most a constant factor. And because we have a 0.5 to the log n over alpha integral solution, if we drop all the zero weight edges, the resulting graph has a maximum degree of delta at most 2 to the log n over alpha, because each remaining edge contributes a 0.5 to the log n over alpha fractional value. Now, using local rounding, what we have seen before in a black box manner, we can compute a constant approximate matching in the resulting graph in roughly log squared delta rounds. Therefore, by combining the key lemma and local rounding, we obtain an algorithm for constant approximate matching that takes alpha log n rounds for the key lemma plus log squared n over alpha squared rounds. For the second term, we obtain by plugging in delta equals 2 to the log n over alpha in the log squared delta round complexity. Now, if we set alpha equals order log to the 1/3 of n, we obtain a round complexity of roughly log to the 4/3 n, as promised. Therefore, what remains is to show that how to prove this key lemma. Then we are done. So the main idea to prove this lemma is that we're going to use a low diameter decomposition of diameter roughly alpha. So before the diameter was log n, now we're going to reduce the diameter to alpha. Now I'm going to say what's the algorithm on a very high level. So first we compute a constant approximate fractional matching x. As a second step, we now compute a partition of the edges such that each cluster has diameter roughly alpha. Now before we have seen that we partition vertices, now we partition edges, but it's very related. It's not important. It's just more natural. Okay, so here we have a partition into 3 clusters. And in the third step, we use this partition to round x to a 0.5 to the log n over alpha integral matching x prime. The rounding, so the step 3, is performed in such a way that each cluster rounds its own edges, so it's responsible for rounding its own edges, without looking at the fractional values assigned to edges outside its clusters. So inside each cluster, we have a brute force computation, which computes this matching x prime for the edges inside the cluster, independent of what is outside. So the question is, how can we ensure if each cluster rounds its own parts, how can we ensure that x prime is still valid, in the sense that each vertex, the weight incident to each vertex, is at most 1. Okay, so this we're going to talk about in this slide. And the way we can ensure that this rounded matching x prime is valid is we have 2 key properties. So one key property is of the partition that we compute. And this partition ensures that most of the vertices are incident to at most roughly 2 to the log n over alpha clusters. So here in this partition that you see, each vertex is incident to at most 2 different clusters. And now assume that it actually holds for all vertices for simplicity. Then the second key property comes from the rounding that we perform inside each cluster. So each cluster ensures that for each vertex, the weight that incident to V, assigned by edges of that cluster, increases additively by at most roughly 0.5 to the log n over alpha. So if there's a vertex and all the yellow edges contribute some value to it, let's say 0.1 before the rounding, then after the rounding they contribute at most 0.1 plus 0.5 to the log n over alpha. So why is this useful? Well, because the 2 properties ensure that the total weight incident to each vertex increases by at most some constant. Why? Because there are 2 to the log n over alpha clusters, and each is responsible for an increase by at most 0.5 to the log n over alpha. Therefore, if you multiply each value after the rounding by a small constant, let's say 1 over 5, we ensure that x prime is indeed a valid matching, and the matching size is still roughly the same. Okay, now let me tell you about the rounding lemma that we use. So the rounding lemma, so that we apply inside each cluster. And I state a slightly more general version. So let x be a fractional matching. We can round x to a q integral matching x prime, where q can be any value between 0 and 1, such that first, the matching size drops only by a constant factor by performing this rounding. And second, if you look at a vertex, then the weight of the edges incident to that vertex, the sum, increases additively by at most order log n times q. The proof idea is that there's a simple and very natural randomized rounding that one can do. And this randomized rounding succeeds with probability strictly greater than 0. And this one can analyze by applying chain of bonds. And then by the probabilistic method, there indeed exists such a rounding. Okay, so that's all I want to say about this rounding. Now what remains is to talk about this low diameter decomposition with diameter order alpha. Okay, so we consider a low diameter decomposition that partition the vertices. So now let's talk about vertices, because this also induces a partition on the edges, into clusters of diameter alpha, such that half, or ideally even all of the vertices, are neighboring at most 2 to the order log n over alpha different clusters. So that's the guarantees that we want to have from this low diameter decomposition. There exists a simple order alpha round randomized algorithm that achieves such a decomposition by Miller, Peng, Flado, and Zhu. And they used it to obtain spanner algorithms. They use this decomposition. So the deterministic complexity that we get for these decompositions is as follows. So if you want that half of the nodes are good, so that half of the nodes neighbor not too many different clusters, then we can achieve a round complexity of roughly alpha times log n. And this decomposition is used for the constant approximate matching. In the variant, or a slight variation of it, then in the variant where we want that all the nodes are good, we achieve a round complexity of roughly alpha squared times log n. And this variant is used for maximal independent set. Some remarks. So the algorithms to compute this deterministic algorithms are very similar to the deterministic log square n round algorithm that we have mentioned before, which computes the low diameter decomposition of diameter order log n. So it's in some sense a generalization, roughly speaking. However, the version where we want that all the nodes are good, this actually requires a new idea to really get a round complexity of alpha squared times log n. So a trivial adaptation would lead to alpha times log square n, but we get alpha squared times log n. And solving this all nodes version requires a new technique which we call pipelining. Okay, so that's all I want to say about the low diameter decomposition. So now let me conclude with some open questions. So first, are there faster deterministic algorithms for MIS? So can we beat the log square n round complexity? One potential approach is to improve the alpha square log n round complexity of the low diameter decomposition that I have mentioned before. So if one improves this, one directly gets an improvement for MIS. While I'm hopeful that this approach that we present here can lead to even more improvements beyond the log square n, I feel that if we really want to get down to a log n round MIS algorithm, this seems to require fundamental new ideas. Then, unfortunately, our speedup does not apply to the more restrictive congest algorithm. So there the state of the art is still log cubed n, roughly. So the question is, can we get a little of log cubed n around deterministic MIS algorithm for congest? And a good starting point is to get a congest algorithm for the low diameter decomposition that I've talked about in the previous slides. That's not the only place where we use large messages. We also use it for the rounding. However, there's some slower version of rounding that also work in congest, at least for matching. And then another question is, can the general framework be applied to different problems beyond matching, beyond MIS and matching? And then I also mentioned this new pipelining technique, and it would also be interesting to see whether this can be applied to different problems. Okay, so that's all that I have. Thanks for listening.